Let's start with updatable fields in Lucene. So today I'm going to cover the current document level update design, which probably all of you are familiar with. The proposed stack design and the current status of the implementation and some implementation details and some limitations of the proposed design. And then if time permits, I'm going to present some other interesting codec applications. About myself, I'm a long-time Lucene user since 2003. I implemented the desktop search. Everybody was doing desktop search at that time. The company went bust, but the application was quite nice. You have to believe me. I created Look, which probably some of you use, the Lucene Index Toolbox. I'm a member and committer of a couple of Apache projects, and I'm also one of the developers of the LucidWorks platform. What is the current design? What is the current model of updating documents? First of all, it's a document level. If you want to update a single field, you have to reindex the whole document. And the old document is deleted. Actually, it's hidden behind the live docs bit set. So for a while, its data stick around, and term and collection statistics are slightly wrong for a while. And then you have to basically resubmit the whole document once again. And you get a new document with new document ID. Right from the start, throughout my talk, whenever I mention a document ID, I don't mean the high level, something like a unique key or application level concept of a document ID. What I mean is the internal ephemeral integer that Lucene uses to track documents inside segments. This integer is specific to a particular segment. It's not changing throughout the life cycle of a segment, but of course, as segments are merged, these integers are changing. So that's why it's ephemeral. So what are the problems with the current design? First of all, you have to store all fields. You've heard probably yesterday that either yesterday or the day before, a new feature was added to Solr that allows you to update a single field. Only it's a fake update because you have to store all the fields in the index, so you can pull them in, reconstruct the whole document, and then apply modifications, and then index this document again. So all indexed fields have to be analyzed again. If you use some heavy NLP processing, if your analysis chain is very costly, then you're going to bear this cost. And especially it's painful if you have large documents with many, many fields that took some effort to collect these fields into a single document. And then you have to update just one tiny bit, just add a label to a document, right? So there are some workarounds. For example, the infamous parallel reader class. It promises that if you have a static index, large static index, then you could have a small adjacent index, secondary index, that you can sort of attach new fields to this main index. But as soon as you start using it, you discover the big problem. You have to use the same internal document IDs in both indexes. And it turns out it's not trivial to make sure that they match. In Solr, you can use external file fields. This works very well for floating point data, like prices or popularity or weights, etc. It has some limitations too. And finally, you can do the application level join, joining documents from two indexes using this high level, application level unique key, or even joining data from the main index and some external data store, a database of some sorts. So field level updates have been sort of a holy grail of Lucene for a long time. And I really wanted to put a nicer picture here. But, you know, the story about Holy Grail assumes that there is a bunch of brave knights that roam the country, fight battles, and pursue the goal, which wasn't the case with field-level updates in Lucene. So it reminds me more of a situation of a first-time father, you know, tasked with changing a diaper. You know, you have to do it. You know, it's going to be messy. You know, you can't avoid it. And you wonder which ends to start with. So my message to you is that man's got to do what a man's got to do. So let's man up and let's do it. So surprisingly, there have been very little research on addressing field-level updates or sub-document updates, as they are called, in the literature. The most recent paper on this it was from 2008. It was a team at IBM that came up with this design and an implementation. The details of their design were sufficiently different from the design of Lucene that it was not directly applicable. But they used very nice concepts, like you have the main data in the index, and then you put, they call it tombstones, but they're just really delete marks. And then you have new data that you then sort of apply. The details were messy, believe me. You can go and read that paper. Here's the reference. Does this remind you of something? It's how the document level updates work today in Lucene, right? So I thought, why shouldn't we reuse this concept, only apply it on a more fine-grained scale to individual fields and individual postings? So based on this paper and based on some discussions on the mailing lists, I came up with this modest proposal, which probably doesn't solve, you know, all use cases, but my hope is that it solves at least some. So, first of all, I wanted to deal with familiar concepts. I wasn't ready to go on a quest to re-implement all of the Lucene. So, I wanted to deal with familiar concepts like documents. I wanted the updates to be expressed as simple documents with fields that contain new values. And then, of course, we have to match somehow the updates to the original documents. So I thought, okay, with Parallel Reader, I would resort these updates so that the internal IDs match. But maybe there's a better way or easier way to do it. Maybe I could, for now, I could store the original document ID in this update and just add it as it goes. So updates would be then written to separate segments. They would exist in sort of a foreign namespace, not in the same namespace as regular segments exist in Lucene, so they are not confused. And somehow then, I would merge this data from the updates segment with the main segment. So you see, I tried to deal with familiar concepts with, and that's actually one of the major goals of this proposal. I wanted to reuse as much of the concepts, models, and existing code as possible. As I said, I'm not ready to rewrite Lucene. So then this older data would be replaced with new data from this stacked segments. The name stacked, well, it comes from the discussions on the mailing list. The paper by Ning Li and the other folks from IBM, they use a term, I think, overlays, because they thought, okay, it overlays the original data. But I think the term stacked better represents, it's more future-proof, because in the future, we may want to stack not only just a single segment with updates, but maybe multiple segments, right? For those of you who came here expecting an existing, a working implementation, I'm sorry to disappoint you. It doesn't exist yet. So this is very much a work in progress. It does not work today, and since every presentation about related to computer science should use a car analogy, it's like a car frame with a bunch of loose parts. So I'm going to present this partial proposal. I also created some parts of this implementation, and I will discuss these parts that I implemented later on. So let's first take a look at writing these stack updates. I have just one slide on this topic because, as I said, we are reusing familiar concepts. Updates are just regular documents, and updates are written to separate segments. And that's all, basically. Only we have to decide whether we want to sort these segments so that the internal IDs match the main segment, or whether we want to add additional field that records the ID of the original document that is to be updated, right? So that we can later on join this data. So the initial design, initial design evolves as I speak, and I spoke yesterday with Simon, who told me that we probably don't need a separate index writer for every segment to record these updates. There is a lower level construct that index writer uses, which is called document writer. And maybe we can have a pool of document writers that create these additional segments. I don't know, you will have to ask Simon. He just volunteered to implement this part. No, I'm kidding. Just do it for fun, okay? So, I can imagine that we would want for the users to have some convenience methods in the index writer, so that you can specify, okay, I want to update document number X, and here's my new data. And the end result of this whole process should be a new segment that corresponds, that stores updates that correspond to a particular main segment in Lucene. So that's as much as I have on the writing part. So we have to figure out what are the interactions between these additional index writers or update writers and the main index writer. It would be nice to support multiple stacked segments. And we have to evaluate these strategies, whether to remap these IDs on reading, or whether remap them in advance and only flush segments that match ID per ID with the main segment. And somehow we have to fit in near real time here. I don't know how yet. So that's as much as I have on the writing. Let's take a look at reading stack updates. We have to combine this new segment with the original segments. So it would be nice if users were able to issue partial updates as they want. One update may contain one field, another update may contain 10 fields, and I could perhaps add another document if I made a mistake with a correction of a previous update, right? So the last update should win, and of course the IDs in these documents that represent updates, they don't match the original document IDs. So we either map or we resort. Let's take a closer look at the first option, which is using unsorted stacked updates. And that's actually the design that I started implementing. So with unsorted updates, we have this ID mismatch, and we have to store the original document ID in the segment. So based on this, since we have these sort of mapping of new IDs to the old document IDs, why not take all of this data and invert the relationship and sort it by old ID? So we get a mapping of old ID, old document that corresponds to new document. right? And then we use a sparse matrix or a map of these matching document IDs for lookup and translation. For example, if you iterate over documents and you want to retrieve stored fields, right? You arrive at document number 10, and for document number 10, you use this sparse map to look up whether there is a new document that matches this old document, and then you retrieve those fields and combine them with the fields from the original document. This map is in memory, yes. The data actually is integrated on the fly, so we don't have to read it in advance. I'm going to explain it later. So let's take an even closer look at how these stacked updates work for stored fields, because that's the easier case. So we have the original segment. We have the documents here, 10, 11, 12, 13. That's the internal IDs, integers, right? And here are the stored fields. If you wonder about the strange values I put there, later on you will get these slides. So you can track it. These values make sense because I used a analyzer that splits character by character to illustrate later on how this works with inverted fields. So this case for stored fields, well, it basically works with any non-inverted fields, so with doc values and norms as well. So we have our original segment, field 1 and field 2. And then we have our updates segment, right? So you can immediately see that internal IDs are obviously different from those IDs. And we stored additional field that records the original ID of the document that the update refers to. And then we have new fields. So for document number 12, we modified field 1. For document number 10, we modified field 1 and 2. For document number 13, we actually added a new field that didn't exist before in this document. And then again, we realized that we have to modify field 1 for document 13 again. And then again, we realized we made a mistake, and we have to update document number 10 again, field 1. So you see there are several versions of a field. These updates are spread over several Lucene documents. And obviously, internal IDs don't match. So, as I mentioned before, we have this mapping. From this data here, we can build this mapping table. So for each field, we have this sparse table that tells us, okay, for the original document ID, the new document ID for field 1 that you should read from is number 4. In this case, why is it number 4? Because the latest update wins. And there have been 2 updates here. The first update was in new document number 1 for field 1, and there was a second update in document number 4 for the same field. So the last update wins here. That's why we have 4 here. So, of course, we are going to use this structure very heavily, and it has to be with very fast access, so it has to be memory resident, most likely. I store it, well, yeah, I could store it, I could sort it like this, but then I would have to expend some effort on flush, right? When I write new segment, I would have to resort it. Maybe I should do that. I don't know yet. This sparse matrix, in this case, I thought that I could, I could recreate it whenever a segment is open. This should be fast because the amount of data here is pretty small. It's just IDs. Sorry? It could depend on the application. It's up to you. Patches welcome, as usual. Okay, so when we combine the original segment, this update segment, and this ID per field mapping table, we get the new stacked segment that we wanted from the start, right? So for document number 10, we have the updated field that comes from document number 4, right, according to this table. And so on and so on. You can check all the details and tell me if I made a mistake later on. I hope I didn't. So let's take a closer look how this works on an example of a single document, right? The previous slide could have been confusing. So we have the document number 10 with these two fields. And for document number 10, as you remember, we had two updates, right? We decided that we made a mistake here and we updated the field once again. So in this mapping table, we have the information that document number 10 has updates for field 1 and field 2. So we initialize this mapping table first when we open the segments. And whenever we want to get stored fields for document number 10, then we check this mapping table whether updates exist for this document ID. They do exist in this case. So we retrieve field number 1 from document number 4 and field number 2 from document number 1. And so on and so on. And if there are any existing fields that haven't been updated, then we retrieve them simply from the original document. And then we present a unified iterator over fields in the end, right? Here. So that was the easy part. Now we come to a more complicated part, which is how to apply the same design to inverted fields. Well, that's roughly the logical representation of inverted fields in Lucene. You have the term dictionary, you have the terms per field, right? And then you have the postings. For each document ID, you have the postings, which is at what positions a term occurs in a given document, plus some other attributes like payloads, like whatnot, offsets, etc. So what is our goal? Our goal is that the updates should update the content of each of this cell in the table, right? So we should get rid of the old positions and attributes, and we should put new data in each of these cells. So now we have this update segment with inverted fields. This is the content of the documents that provided this data for inverted fields. So you can see, for example, for document number 0, we have a field 1 that contains these terms, and they have been, for field 1, at position 0, we have term B. At positions 1 and 3, we have term A, right? And you remember that we recorded that this document refers to the original document number 12. Which is actually good, because then this means that we can reuse the mapping table, which is very nice. We don't have to build yet another structure. So we have this ID per field mapping table that we are going to reuse. And we take the latest postings at the new document ID. So you remember, for document number 10, we had 2 updates, and only the latest should win. So that's what we do. We discard the updates from document number 1 for field 1 because they are obsolete. They were superseded by updates in document number 4. So based on this, we get the new postings here, which are a combination of this original table. Again, this is a logical representation. It's not actually how the data is represented and how the data is accessed in Lucene. This is just to understand what's going on. And using this ID per field mapping, we put the right stuff at right positions, right? So, for example, this cell, the data from this cell for term A and field 1 and document 12, and it's up here, right? That's easy. yes, I'm going to discuss this as well. So, so let's see how this works on an example of a single document. Again, to simplify those tables. So first of all, as Uwe said, we need merged enumerations for terms and for document IDs. How do we do that? Actually, I'm going to explain in a moment. But let's assume that we can do this, that we can have merged enumerations of terms and merged enumerations of documents. Again, we reuse this mapping table. We position our cursor, our current position at document 10 in both of them. And by the way, we realized that, okay, there are updates for document 10 based on this mapping table, right? So for document number 10, we see that there are that we have to discard the original postings for terms, and we have to insert postings from the updates for document number 4. And that's it. So we retrieve the postings here, and we insert them here. You should note that this is the major cost of this approach, because enumerators don't jump freely. So you have to actually recreate enumerators here in this secondary index. And this, basically, you have to implement random seeking on enumerators. So that's the major cost of this approach. And then we advance to the next doc ID, and we repeat the process. Yes, I thought about the concurrency, and again, I'm going to explain it in a moment. So a little bit about the implementation details. As far as I actually implemented anything, I extended segment infos to keep the information about this additional stacked segment, obviously, so that whenever we open a new segment reader, or actually segment core readers know that, okay, they should open also another segment, and they should create various format producers. That's the Codec API stuff. And then they should initialize these stacked producers that combine this data on the fly. And also they should initialize this mapping table that is a shared structure among these different producers. So, yeah, how do we merge this using the Lucene APIs, which are not so nice to access? They don't provide so much random access as these table illustrations that I showed before. So, when it comes to the list of fields that are present in a segment, that's trivial, because that's very little information. You can merge it on the fly. Stored fields producer merges very easily, because as soon as you know what fields there are, as soon as you know what is the target document ID, the new document ID, then you simply retrieve fields that are stored at the new document ID, and merge them with fields from the old document ID, from the old segment. So that part was really trivial. The implementation is like 100 lines or something like that. However, terms enum and docs enum enumerations don't merge so easily. So what to do? Well, I implemented something that I call leapfrog enumerators. Obviously, we don't want to read all this data in advance, because that would be too costly. We would have to basically store all this data in memory. That's not possible. So this leapfrog enumeration works like this. First, we initialize both the main enumeration. Let's say we work with terms enum, right? We initialize both the main terms enum and the stacked terms enum for a field. And then we return from the smaller one. We use the comparator, right? The comparators should be the same, obviously. And we keep returning from the smaller enumerator, advancing as it goes, until it reaches or exceeds the other enumerator that was larger so far. So if values are equal, then we know that we have to merge. If, and again, in this leapfrog fashion. And then we advance both if they were equal, and then we see which one is smaller. And then, again, we keep returning from the smaller until it reaches the larger one. Deleted terms. Well, if deletes are not expunged from a segment, then terms are not expunged. So, yeah, terms are still present. It's just hidden at a different level using this live-docs bit set. Yes, it's very similar, right. The details are slightly different, but again, the concept is the same. So for your enjoyment, we have leaping frogs here. Right, what about segment merging? Well, it turns out that we spent so much effort on making these enumerations work that segment merging is trivial, because all of these changes, all of this merging is now hidden behind the Codec APIs. So we just merged, and the data magically falls into the right places, and we end up with the resulting segment that has these updates rolled in the right places. I'm told I have 5 minutes to go. Yeah. Okay. 7 minutes. Okay. Good. So limitations. Obviously, there is search time costs involved in this, and this mapping table will consume some memory depending on the number of updates, even if we use sparse and compact representations. There are overheads. There is a lot of random seeking in the secondary index. So preferably, if we could fit these updates from the secondary index completely in memory, that would be ideal. So there are some trade-offs here. Generally, I think the conclusion should be that using this design, the updates should be kept to a fairly small part of the main index. At least small enough so that most of the structures will fit in memory. I don't know how this is going to work with near real-time updates. Maybe it will work. It will just work. I don't know. What I know for sure is that we don't have to rebuild this mapping table completely. We only have to update the individual cells. What is the current status? As I said, loose parts around. So don't expect that it's in a working state. This is the JIRA issue number. If you're interested, please check it out. There is a branch in Subversion, so hopefully you feel encouraged and you feel certainly invited to take part in the development. And there is some initial code for these codec producers and segment infos changes, etc. And these enumerations. Help is very much needed and is welcome. So this obviously needs to be continued. We need to evaluate the cost of this runtime remapping. We have to extend the design to support multiple stacking, and we have to handle deletion of fields because what I illustrated here, it was only to illustrate how to modify or add fields and not how to delete fields. Briefly, in one slide, I will mention the alternative, which is sorted stacked updates, where we, on each flush of this segment with updates, we resort the segment and we synchronize IDs with the main segment. Well, essentially, this is the parallel reader approach. So it has the same pros and the same cons. And actually, cons are probably prevailing in this case. Updates arrive out of order, and we have to also combine multiple updates from multiple documents into a single document because if the IDs have to match one-to-one, then we have to have a single document containing all the updates. So basically, for every update, we have to completely rewrite and resort this stacked segment, which is not nice. I suspect that implementing this would be more costly than this runtime remapping. So reading these sorted updates, well, it's a variant of a parallel reader that simply returns the latest data instead of combining data from two readers. So again, this JIRA issue describes the design and has some patches, and it implements this unsorted design. I don't know if within 3 minutes or so I can cover these other codec applications. Let me just say that implementing this became possible only because of this Codec API, and only because this Codec API now is complete. That is, it covers all the parts of the index. Otherwise, it would be very, very difficult, really. But there are many, many applications, exciting applications that are possible with this Codec API. For example, I implemented a T-codec, which is writes data as you keep indexing. It writes data to multiple locations, possibly using different encodings. And there's also a little utility class that I wrote, which is a T directory, that simply mirrors the data that is still not handled correctly by the codecs. So, for example, you can use T directory separately. This part is actually implemented, and it works, and there are even unit tests for it. So, T directory is simply mirroring data byte by byte. So you have the main directory, and then you have a bunch of other directories that you can write the data synchronously to all the locations. Another application of codecs is the filtering codec, which does what the name suggests. It simply filters out some data as you create your index, as you keep indexing. So, for example, you could get rid of stored fields, or you could add stored fields, or you could eliminate some postings or some terms, etc., etc. One example of that combines all of this together would be index pruning, which is on-the-fly pruning. There is another package that is in Lucene, which is a post-processing type index pruning. So this is on the fly. It happens as you keep indexing. You have a filtering codec. T-codec splits the output to two locations, right? And then you have one small, fast SSD-based index that handles most of the queries, most of the volume of the queries. But for certain queries, you refer to a much slower, but a complete, huge, total index, right? And another example that is, again, implemented and it works is a single-pass index splitter. In this case, T-codec has multiple outputs to several filtering codecs. Each one has a different configuration, so it selects a subset of data, not necessarily disjoint, and then it writes to multiple locations. And that's how you get splits in a single pass. That's my last slide. So, as I said, this is the initial step. Somebody had to do it. I don't know if I'm the best person to do it. I don't know many details about Lucene internals that I should probably know in order to implement it. So I hope others will join in the development. Thank you. Any questions? The question was whether it has impact on Lucene caches and Solr caches. Yes, it has, as every update. I mean, you have to reopen the segment, and obviously, as you reopen the segment, then you have to invalidate caches. Yes. One more question, I'm told, so I'll be around later on. So the question was that the field updates in this use case they affect a field that is used for faceting. So what would be the performance impact of using these field updates on this particular field? The short answer is, as Uwe suggested, you should use per field faceting, per segment faceting, sorry. But then again, for these segments with updates, I have no idea. As I said, it's not a fully working solution yet. It's just a design that needs to be evaluated. So once it starts working, please grab it and evaluate it. Thank you very much.